Ladies and gentlemen, I hope you enjoyed the break. And in a moment, we would like to resume the conference. I hope you have a chance to recharge, to refresh yourself. And I hope you will not suffer from the gastro dementia after the lunch. Okay, so if you could please make your way back to your seats, we are ready to resume in 1 minute. Thank you. Ladies and gentlemen, I would like to introduce our next speakers, Mr. Robert Shalonsky. He is an engineer at BMW Group responsible for body and long-term testing as well as measurement techniques in total vehicle testing. He leads the RoboCT program within the BMW and brings decades of experience in mechanical engineering and automotive testing. Together with him, I would like to introduce you Mr. Thomas Meyer. He is an engineer at BMW Group specializing in non-destructive testing and high voltage system within vehicle testing. He has been working within the team method since 2001 and is certified across a wide range of inspection techniques. Their talk is titled RoboCT in Total Vehicle Testing at BMW Group. Gentlemen, please come to the stage. The mic is yours.
We have a fully automated BMW engineered and developed hoist where we can really completely hoist our heaviest and tallest cars. As you can see in here, we are really capable to carry our tall vehicles with open lids and doors to go with the robots around and around and go for an entire testing of all the possible areas around. We developed our cell in 2018 and we started the construction in July, and just before Christmas we got the first images, which was a really tough time schedule what we had over there, and we brought about 400 tons of material inside an existing building, a very tiny building. So our shelter, our X-ray shelter is really very fit into our building. As I said, the hoist system, we had the first Hamamatsu microfocused tube in Europe. And then we integrated the stereography, the thermography, all in one test cell, which enables us to really go on the different tasks for our testings. We have a lot of storage capacity with the GPU servers, with the graphic cards, and everything is completely integrated in the PLC of the control unit. So we do have an exhaust system so that we can even run vehicles on a combustion engine and can absorb the exhausts. So this really enables us to do everything in that cell with non-destructive. Why are we going to do this? We have really changing requirements, because our cars are on a worldwide testing, and our main focus is really test and validate the vehicles from the motorcycles up to the Rolls-Royce brand. And with each car, we do have different tasks and different requirements what we have to look at. So standardization is not our biggest topic. That's also the reason why we cannot go for simulation up front or for doing everything, the simulation. So we really have the task at the car, and we have to focus, can we really reach the areas, which is the best method to detect, to find the failure mode, and then decide which is the test method to go ahead and possibly try to keep the cars up and running, so not to disassemble the cars and take it out of the test program. So really use it during the test program, bring it in, make the scans, make the images, and then hopefully can identify what's going on, and can then, together with our development departments, find issues and root causes, and can hopefully find all the possibilities to repair systems or to exchange the parts. And first of all, normally we're doing just an X-ray picture so that we have just an idea where the failure mode could be, as you can see on this small picture in the middle. And then we find out that something happened at the wiring, and then looking with a CT still at the car, there is a broken wire, and that was the reason why we had a malfunction at the car. And this is our main focus using that cell, and we are using on a day-by-day usage in our cell, and you can see it is really since 2018 or 19, beginning of 19 in use. You can see that we have inside components, we have electrical components, we have water ingress, corrosion anomalies, seal passes, PVC coatings, and this is a various range of of problems and failures which could happen in a total vehicle testing, which is still our main focus to really carry on this one. And this is just a support for that. Yeah, and to see what is really feasible and what we have done in the past, I would hand over to my colleague Thomas, and he would show you a few examples which we had in the past and which enables us to bring this RoboCT technology into a really absolutely common use within BMW, and nearly the entire company asking us, can you support, can you have a look at that? So it is an established technology right now within our group. So Thomas, please.
So hello everyone, also from my side. After our system was completely built up in 2018, we go into internet communication within our organization, aim to integrate our new possibilities to our total vehicle testing. But this turned out to be more challenging than accepted, as existing processes and mindsets have to be changed, and we don't have any motivation examples actual. This situation changed when a supplier reported an issue in a component located deep within the vehicle structure. In this case, classical analysis methods would have been very difficult to apply and would have significantly delayed validation time. In addition to supporting the project, this presented an opportunity to demonstrate the capabilities of the test cell and to generate an effective communication tool. For those who are wondering why Toyota vehicles appear in the image, these models were developed as part of a cooperation between BMW and Toyota. While the first vehicles were being shipped to us, we used the time to carry out principal tests on comparable components in order to determine suitable parameters for the RoboCT. Here you can see the first trial picture. And after these tests, the components were removed and verified by sectioning. This confirmed that the method is functionally suitable. So following by the component tests, the first trial were carried out on a complete vehicle to determine the robot trajectories and the very confined spaces. And after several optimizations and positioning the vehicle on the lifting platform, a stable process flow was established for more than 100 vehicles. Once all settings were finalized, multiple scans were performed on reference components and as well on several vehicles with reference bodies inside and defective parts. Those were subsequently analyzed with destructive methods afterwards. And in case of the complete vehicle, this meant that they were physically cut open. At the end of all tests, the results led to an analyzed method that fully met the requirements for approving the vehicles for public road testing. And the positive side effect was the increased visibility and acceptance of the modular test cell. No one questions why should we use the cell, but instead the only question was why we have time for an analysis. The situation has not changed until today. And this brings us to a more recent example. Here we see a new model in which a sporadic fault occurred in the door handle. The issue could not be identified through diagnostic or even by disassembly. It was suspected that the problem was related to moisture ingress. Here a short impression how we work in our test cell. This shows where the vehicle is put on the lifter. And so we get the first X-ray pictures, followed by an analysis of the pictures. In this case, only a rapid in situ analysis where the vehicle was exposed to different climatic conditions and then immediately viewed by X-ray in the pre-programmed test cell, it was possible to temporarily detect moisture accumulation inside the door handle motor. And the X-rays images in original show slightly the effects better. Within a few days, we were able to develop a corrective measure to resolve the issue. This is the benefit of the test cell. And the last example shows the flexibility of our system. During a technical discussion on site, an expandable foam part with sealing issues was mentioned. Fortunately, a sample part was available. And the component was quickly placed into the test cell, and a rapid CT scan was performed using the rotary table functionally. Here you can see the technical expert result on the left side, and on the right side, the management level result. We see here air inclusions that already are present in the raw part, which led to leakage issues during the process. So these were the examples for our test cell, and what is the summary? Our test cell is a fully integrated test entity within the validation since 2018, and we offer our service to the entire company within quality assurance process. Thank you very much.
Thank you very much both for your insights, for insights of users, of RoboCT users and also developers, definitely. If there are any questions to gentlemen, please don't hesitate.
Good luck.
Yeah, I see one raised hand here in the second row.
Thank you for your talk, very interesting. So it was interesting how you found that broken wire.
Yeah.
But that was, one component in thousands in that car.
Yeah.
How did you identify, did you have to scan the whole car and look at it? How'd you find that one spot?
I mean, sometimes really we had the challenge that the guys tell us, hey, can you scan the entire car? This will never happen. So, no, what really goes on, so we try to identify where could be the area, and then we also try to use the most appropriate method to look at it. And sometimes, I mean, for the example, on this wire harness on the door handle side, what Thomas presented you on the car, so we did not really know where it was, but we had the area around the door handle, and then we really run with the X-ray through that designated area or the suspect areas and find then out, okay, it is nothing at the wire harness, is it nothing at the connectors, it has to be either on the motor or on the mechanics, and then we come even more to the details and find out where it is at the end of the day. So this is always the case. We try to use the best method, and that's the reason why we have integrated all the different non-destructive methods in that cell, so that we are really capable to put the car in the cell and then use the most appropriate method for it.
Okay, thank you.
Welcome.
Thank you very much.
Okay.
If no one else is about to ask question, thank you very much for your presentation.
We have to say thank you for that. See you then.
Thanks. And now it will be my privilege to welcome again Professor Gabriel Erl with his presentation. As I said, Gabriel Erl is a professor for robotic computed tomography here at the Deggendorf Institute of Technology, where he has been advancing robotic CT research since 2015. His work focuses on CT trajectory optimization, calibration, and automated workflows for industrial inspection. In his talk titled RoboCT in Deggendorf, Next Steps Towards Automated and Flexible Robotic CT, he will explore the next development steps in robotic CT. Dear Professor, the stage is yours.
Thanks. Okay, hello. Okay, I want to talk what we are doing in Deggendorf right now. We want to go to full 3D robot CT. And I want to start with an example. Here we got a rear subframe from BMW, from Landshut. Many thanks to Noah Stöckl that I am allowed to show it. The background is that there's a new BMW iX3 series available since March this year. It was tested extensively on the racetrack, and now they wanted to know, hey, can we expect this without destroying it? The object is an aluminum integral casting, size 1.3 meters to 0.85 meters. And the goal was a complete 3D scan, not just laminography, tomosynthesis, no limited data CT, no complete CT. And yeah, so we did it. And yeah, here you can see the result of the CT scan. Yeah, it's quality like a normal CT. We scanned it in 20 regions of interest and then combined them. So it was a little bit of work, but I want to show that it's possible to do CT on big objects, and if you have the time, then this is totally fine. Maybe another time. So we did it on 20 regions of interest. Each region of interest we tried to do pretty well, with 2,400 projections, 3K volume, voxel size of 325 micrometers, 2-hour scan time, 2-hour calibration time, so in total it was 80 hours. I mean, I think it's cool that we are able to do it, but for me that's too slow. So we're working on flyby CT for a long time. So we tested, hey, can we do this faster? And so we compared it. For the scientific method, we compared it on a subregion of 35 to 90 centimeters. So that was about 5 regions of interest. So in the normal approach, it would take 20 hours with a stop and go. And with our flyby motors, with a helix with 7 turns, it could be scanned in 50 minutes and 20-minute calibration time. And so the complete object could be scanned in about 2 hours. Obviously, the image quality isn't as perfect, but depending on the quality, and obviously we're refining it right now, we can do RoboCT, complete 3D on big objects, and soon pretty fast. And what we're doing in detail, I'll start with robot path planning. That's mostly the work of Anton Weiss. If you want details, go speak to him. It started with the expectations. Normally, if a user or customer comes to us, he expects that the robot problem is more or less solved. The expectation is often that you just define a region of interest, find some good X-ray parameters, say, I want this kind of trajectory, and then go, and everything is fast. It follows a given trajectory, and obviously you don't have collisions. In reality, obviously, that can be difficult. You can see here our digital twin, and maybe you can see that here probably there could be a collision. So we look at another slide. Yeah, there would be a collision. So what do? The approach is an in-house implementation of a custom collision-free SQP trajectory planner. There's a lot of math involved there. Obviously, we need some constraints, some soft constraints. The idea is to use as many axes as necessary, but as few as possible. So we could use linear axis, turntable, and the joints of the robots. Obviously stay close to the reference trajectory But if there's a collision, obviously we want to deviate a little bit. When there are hard constraints, obviously the joints are constrained. We have min and max limits. We have higher order limits. We don't want to have extreme high velocity or acceleration or jerk. So there are some hard limits. And obviously we want to be collision free. To achieve this, we measure a lot of different joints, positions, orientations, and compare them and try to optimize to stay in the limits and be close to the given trajectory. For details, ask Anton later. What does it mean in reality and how does it look? And you can look into the RoboCT. There's an interactive way thing of this too. Here on the right corner, you see the given trajectory that has a collision. And then on the left side, you see the corrected trajectory. And here on the bottom side, you see that it can really be done. So this is with a rectangle object as a safety collision object, and then just a scan of a test object, of a standard test object. And you can see it's a smooth motion, does something sinusoidal, and it's a flyby scan. And here, in this case, we compared it again to stop and go and flyby. And here on the left, you probably won't see a difference because the difference isn't that big. You have to look at it very close to see the difference. But we could scan this thing in 10 minutes with 3,000 projections and flyby. The same thing took 2 hours, 15 minutes with a normal stop and go approach, because in fact, a lot of the time goes missing by robots that go to the next position, maybe don't do it ideally. So we could need 2 hours, 50 minutes. Now with a new flyby approach, it can be really fast. The RoboCT doesn't have to be slow. And the key metrics of this method is that the calculation is in under 1 minute. It's fully collision-free. It's optimized for scan speed, so not just the shortest trajectory, but the fastest trajectory. The operator can select a region of interest. And it's rather efficient, up to 10K discrete poses on a 16 gigabyte GPU. And currently ongoing work is that we do it in a model predictive control method. The idea is that we can optimize and adapt the trajectory or the robot path during the CT scan itself to react on the scan data. And this is relevant because obviously not only the robot path is relevant, but which views do you need in the first place, so the scan trajectory. And this is the work of Simon Whittle. There are already several methods to optimize scan trajectory, so to choose the views that are necessary. And earlier methods often look like this. This is from my old PhD thesis. And this has some problems. First, it is optimized for stop and goes. There are some discrete views. And obviously, how do you go for these different views in a smooth way? So every dot is a source position for the trajectory. Often trajectory is task-based and therefore has a task-based bias because you need to know the defect or the stuff that you want to optimize your trajectory for. So that's a problem. And obviously computational speed. If you have discrete views and you want to have a nice trajectory, then you have to check a lot of discrete views in the 10,000s. And this was my old method, and Simon Whittle improved it. One way he improved it is with reinforcement learning for an automated robotic CT that doesn't need any prior knowledge about the object and doesn't need a user to say, hey, I want this kind of trajectory. The idea is that he implemented a TUI-informed real learning agent. So it tries to get a data-complete trajectory based on the TUI conditions. It has kinematic awareness, so it knows which positions are okay and which aren't. And then he did training. Training lasted about 3 weeks with about 40,000 unique scenes. And the scenes were made by up to 5 randomized objects. And you can these scenes here. So really different objects from internet database, just combine random objects and try to learn what are the best trajectories for it. For the technical implementation, if you're interested that deep, please ask him directly. So what can I expect here? So we had a test object that's very recent from Project Sonic. I will talk later about Sonic. Here we got a part of a leaper, of a crane. And in the future, we want to scan this non-destructively with a mobile RoboCT. For now, we had to just take a part here and place it in our RoboCT. And yeah, Simon took this part and placed it in the RoboCT and just activated this reinforcement learning agent and started the scan. So no trajectory was given here. The RoboCT goes in a position, starts scanning, and says, okay, I think based on this projection and this knowledge that I have, I need the next movements. And here we see the projection. The lighting isn't that great. It's a good projection. And we see that the robot starts moving, the turntable is moving, and it avoids the long penetration lengths and does something like a tilted circle. To be honest, it's rather difficult to understand the trajectory here because the turntable is moving and the robots and everything. So what in reality happens, something like this. So this is like a tilted circle, and in the end he adds this small circle. So he gets a circle and then he adds some information up and down to reduce cone beam artifacts. And the real agent, the reinforcement learning agent, did this totally on its own. We didn't say, hey, make some circle and add something. This is the result. And this isn't a special result. In fact, Simon got this part last week and did his scans on Monday and Tuesday. So it was just a cool object, put it in, start. And yeah, CT scans look quite fine. I don't know if you can see it with the lighting very well. We can see defects. Yeah, I think a normal CT user couldn't do it in a better way. So yeah, we're quite happy with that. Obviously, this was a small part. For bigger part, it's obviously more difficult. We have to see which kind of positions we can reach. Yeah, it makes it more difficult. So another PhD student of mine, Jonas Schnitzer at BMW in Munich, did a simulation study on a car body of a BMW 4 Series. He placed it in the digital twin that mimics the RoboCT in Munich. Placed at 60 centimeter high, robots and full CT cell were simulated. He simulated at 273 regions of interest. Evaluation was with 4 discrete linear positions on the linear axis, no turntable, and he said it's data complete if the trajectory, the circular trajectory is more than 220 degrees. And in fact, I was surprised, but for most of the cars, this is in fact possible. It's not possible at the end. That's due to the size and space of the digital twin at Munich. But it is in fact possible. However, that doesn't mean that we can have great CT images at these places because often the one robot is below the car, one is over the car, and the penetration lengths are too high. But yeah, that was the results of Jonas Schnitzer. And the paper should be there soon, I hope. Okay, so yeah, we can do a lot of CT scans. It's really a lot is automated. Now often questions about speed, about reconstruction. We're doing a little bit in this direction. One topic is of Alexander Jung, another PhD student. Here the idea is that often we prefer circular trajectories. Circular trajectories are easier and faster because we can use analytic reconstruction. However, often, obviously, we can't do circles, but we have to do strange stuff. And here the idea is, hey, I want to have the source on a regular circle, but the detector might be allowed to do strange stuff. And this would look like this, for example. The source goes a normal circle, but the detector is allowed to shift and to rotate. So this could look like this on the projections. And his approach then was to include a virtual detector, and he projected the real detector on the virtual detector. Oh. Yeah, does it start? No. Yeah, okay, it's not exactly the same, but you see on the left side, the detector makes strange motions, and on the right side is a virtual detector that, yeah, just has the normal position, and then we can do fast FDK reconstruction even when the trajectory of the detector doesn't follow a perfect circle. Okay. So this is more or less the stuff that we have done or, yeah, working on. And now I want to show some projects that we are starting right now or in progress. One is Project Sonic that I already mentioned. It's together with Phil and some other partners. And the goal is here to go mobile. We plan to go mobile too because, yeah, small mobile robots are cool. And we want to combine it with laser ultrasound. And we want to, yeah, find efficient, precise inspection workflows. We want to do joint reconstruction. And we want to test it on several use cases, such as hydrogen tanks or cranes. Another project in which we want to go mobile is a project CT4 Pro. That means CT for production. And we want to do it with a 4D workflow. So we learned to be faster, and now we want to learn to be still faster and want to look at production processes, and maybe we can see some stuff with time resolution. And in our first test, we scanned a microwave that we put into the RoboCT. We turned it on to dry a building stone, a building brick. And that's a normal process. You have to dry bricks, and if you do it wrong, then there will be cracks. And the idea was to see how the crack forms. So we scanned the microwave while it's on. We could see some time resolution. Yep. Okay, that is more or less what I plan to do, and I will try to be fast so that I can talk about another topic, CT for bridges. That's a project that we have together with Sebastian Schulze from Bauray. He should be speaker here, but like I told earlier, he couldn't come due to health issues. So I want to say something about bridges and CT. So obviously, collapsing bridges are a problem, but it's really difficult to do the condition assessment. There are a lot of different possibilities, a lot of different defects. There are methods like ultrasound, like radar, but And we have a lot of aging bridges. This is an example for German railway bridges, and there are over 14,000 railway bridges in Germany that are more than 100 years old. So do you trust them? I don't know. And obviously there are a lot more bridges, normal streets for normal cars. So, hey, when we can do CT with shaky robots, and if you can do mobile CT, what's maybe one of the most important things to scan or to test? Hey, that could be bridges. So we have project Brücken CT, it means bridges CT. And we started with a feasibility study together with VisiConsult and BAM and Bauray and TUM. We got a Betatron from BAM. And then we scanned a test object. It's like a realistic test object with some steel segments in there. We could find defects. We could segment the metal, so in the lab it works. But okay, that's not that cool, so let's go out there. And Bauray, Sebastian, makes a lot of X-ray scans on buildings, on bridges, and we can really see into this stuff. But obviously that's just 2D. And now we test, hey, can we do real 3D? Or here we have to obviously go for laminography because can't scan around a complete bridge. And here we did scans at a bridge near Würzburg, a big bridge. You can go inside the bridge, so there's a box girder, and here is the source is inside it. We put the detector outside of the bridge, and then we started scanning. Here in this case, we really, by hand, placed the source at a little bit different positions to achieve something like a laminography, but really ugly. But for a first study here on the left, we have a projection of a couplet joint. Here on the right, we have a tomosynthesis, but a really ugly one. But it's the first study, and we're trying to get more experiments and see where it goes. I think it's really promising, and I hope that it's worth the effort. Yeah, that's it from me. So thank you very much. Thank you all that you're here. And if you're interested in some scans or interested in support with RoboCT or your own RoboCT, talk to us, write me an email. Yeah.
Thank you very much, dear professor. And I'm sure there will be some questions. Yeah, thank you very much for your first question in the first row.
Yeah, the world changes and you can do a lot. That was very interesting.
Thanks.
But coming from the old CT, the part from the crane, I typically would make a spiral CT to get rid of the cone artifacts. Why did you change it? Did you select another scanning method?
I didn't change it. The reinforcement learning agent did it. And he did it because he didn't know the part. He just started.
Talking on the crane which you had in the laboratory.
Crane?
Did you show a movie? The crane, der Kran.
This crane object was this object.
This one, yeah.
Yeah.
And normally I would take it on a turntable and rotate it in a spiral for a spiral CT. You made a different...
That's because you know how the object is shaped. The reinforcement learning agent didn't know it and just started. And then in the end, he said, okay, now I have this, and maybe I lack some information here and some here, so I go up. And then I say, hey, I missed some information here, so I have to go down.
Okay.
So it was not a planned movement, okay, and it might be better to just start here and do something like this, you're totally right. But the AI just did a circle and say, okay, here and here I need something and go. It's not perfect, but it's pretty good and it's automatic.
Okay, thank you.
Thank you.
Thank you very much. I think you were very clear then.
Thanks.
Okay, we can go one step ahead. Thank you very much for the presentation. Very insightful. And our next speaker will present a talk called RoboCT for Large and Complex Components, from Early Systems to Automated Inspection. Ladies and gentlemen, our next speaker is Mr. Markus Eberhorn. Welcome, Head of Group CT/MT at Fraunhofer Institute for Integrated Circuits. This talk will present the evolution of robotic CT system over nearly 2 decades. A key highlight is the transition toward fully automated inspection workflows for large-scale and complex components. Markus Eberhorn has been developing industrial CT systems for over 2 decades. His expertise spans system architecture, prototyping, and application-driven design of advanced X-ray inspection systems, and more by himself. Thank you very much.
Oh, thank you very much for the introduction, and hi to the audience. So, my talk should be more or less about the automatic system, but I have to change a little bit because we have we are running under NDA restrictions, so I could not talk too much about the automated system. So I have to switch a little bit my presentation, and now we have an audience who knows, most of these people are here experts in CT. So my classical presentations about RoboCT, I try to tackle bias against RoboCT, that RoboCT is complicated to operate, missing precision for high resolution CT, or RoboCT systems are too expensive in operation. I think we heard already some impressive talks about RoboCT and what RoboCT is now able to deliver for different applications. So I changed my presentation a little bit in a different way because we are now finally at age of 18. So I checked what was the first presentation, the first talk we give about RoboCT, and now I would like to give a talk about a trip down in memory lane. So in Germany, it's like tradition, if you get the age of 18, you will hand over some paper photo book about what is done or what has happened in your life. So first, I will start about some words about Fraunhofer. I'm an employee at. Then I will go to the photo line, the trip down in memory lane. Then I also brought some pretty nice images from the scientific center, from our RoboCT lab, and a conclusion. So Fraunhofer is one of the biggest research institutes in Europe with almost 30,000 employees. And we are public funded with 30% and 70% we have to acquire on public research projects or in industry research. With one restriction, we are not allowed really to sell products. We develop prototypes, and we are allowed to sell prototypes in a different shape, but we are not allowed to sell systems again and again in the same situation. In total, 76 institutes, and I employee at the Fraunhofer Integrated Circuits, IAS. So what is Integrated Circuits doing with X-ray? So that time, electronic components must be also tested, and this was also the situation where the EZT and the Fraunhofer Institute for Non-Destructive Testing in Saarbrücken decided to build a kind of virtual department, and this is the Development Center for X-ray Technology I'm working for. And yeah, we have several locations, one here also in Passau, a joint venture with, or co-rated department with the THD, up to Würzburg, and our base is in Würzburg, and yeah, pretty nice cities, and at this point a warm welcome for some sightseeings and also some scientific scenes. So these are all the systems we have from Würzburg to Deggendorf and in Fürth. So we have in total something about 25 CT systems in different shapes, different styles, different resolution. For example, one thing is at the right top corner, we have our high energy system. This system is able to scan a complete car. So we saw already some pretty nice pictures from Robert Schalowski. So, yeah, let's start the trip down in memory lane. So some steps we walked in developing RoboCT technology. Yeah, the first thing was the motivation. Why was the motivation to build some RoboCT system? And the motivation comes, I think Mr. Uwe Ebert knows very well, testing large aerospace components for new composites aircraft such as the Airbus A350. That was the motivation. And the question was, yeah, how could we bring a CT system to airplanes? And the idea was born in 2005. I think digital radioscopy was not really allowed at that time in airplanes or aerospace testing infrastructure. So who knows Mr. Randolph Hanke, the former head of the EZT? Yeah, he likes word arts, and that was his solution. He put some word arts together and said, yeah, airplane, some robots. And in 2007, we started the first feasibility study with Airbus, and we built up our first mobile on-site RoboCT system. So at the time, we were very happy. So these are Casper robots. That was medical robots for operation, but this was restricted by the FDA. So these robots were very at low cost available. So we bought 2 of these robots with the company Robotechnology and build up our first RoboCT. That was 2 Stolpe robots, mobile with a Comet MXZ. So that this time already is an HP11, one of the first tubes that were built, and Hamamatsu detector, 100 micron. And we were quite happy on the top right side. That was the first computed tomography Feldkamp reconstruction we performed with our RoboCT. And we also did some RET reconstruction that time. So I think Alex Jung was already involved that time at Fraunhofer as student. So the first RET reconstruction that time took something about 2 hours or 2 days of calculation time to get a feeling about what changed meanwhile. Yeah, we were a little bit under pressure because there was the International Symposium of NDT in Aerospace 1.5 years later. And Randolph says, I need first results and we have to do a presentation, and it was the presentation. So what we did after this time, from 2007 to 2012, we learned a lot about robotic tool center, mathematics about how to handle robots, to optimize robots, what is Cartesian move, what is mechanical move. So we do a lot of effort in algebraic reconstruction, because if you have arbitrary reconstruction trajectory, you have to be able to reconstruct this kind of data. So we spend a lot of time, application studies. We get out of the building, ask for applications, and the most application, and we are focused on that time, was aerospace components and doing on-site inspection. Then there was some issue for some company who were building up airplanes, and then the race was won at the bum with the Tomoka. And we feel a little bit sad that time. So then with the move from the old building, from the Fraunhofer EZRT to the new building, we have a huge X-ray cabinet, and we started looking around what could be other applications, and nearby is the company Audi. And we did first scans for Audi on the car body. Yes, and from the time 2012 to 2015, we run in Qualcomm a project for large-scale X-ray RoboCT and large-scale inspection with X-ray testing on aerospace components. So, Thomas, we know very well how to be precise here, Accubots really, and doing first CT applications with first results in 2013 to 15. So, that time everything was a black box by sight. So the first CT scan we performed was clicking the neck position, saving an image data, and that's 500 to 1,000 times. Took us a complete day for the first reconstruction we performed. By sight, and this was very great for us because we showed good results on the car body, and then on somewhere around 2015, we got loaner robots from Audi, and we built up our first full-scale stationary RoboCT system. And question to the audience, guess who did the race, BMW or Audi? I think we know already. Yes, so we did the first CT scans left on the Accubots at FACC. And this was already supervised or mirrored or accomplished by BMW at that time, so with Peter Janke. And that was a great moment, a milestone for RoboCT development for us, because BMW did the decision to work with us to build 2 RoboCT systems. And that was very, very amazing situation. So now we have the funding, the budget to put all puzzles together for a first industrial style RoboCT application, where you don't have to be a robot CT or a robot expert. So it could be used like a typical CT system. We build up the digital twin. That's the system is located at the prototype plant in Munich. And the system you already got presented from Robert and Thomas. That's the system who is built up at Eching. So with these 2 projects, so we are a non-profit organization, and now we have the budget to build up our RoboCT system in our new building. So now we have 2018, we built up our first RoboCT system with linear stages, with 2 3-meter arm length KUKA robots, and with the first prototype of the mesofocus tube. So we ran the first scans with the variofocus, and very quickly after this, Comet gives us a call, so hey, we have a new type of source. Are you very interested in it? We say, yeah, why not? So we run with the variofocus, the first mesofocus tube, and now we are able to generate huge pretty images. My colleague Wolfgang spent hours and hours at the RoboCT system and generates impressive images. So, and we have also go ahead bringing all the applications we have at Fraunhofer together that works together. We have an RDR software, we have reconstruction, we have tools for trajectory planning. And yeah, we run also our application center at Fürth, and we also do a lot of applications with our RoboCT. I will show some results later. Yes, in 2023, more or less, or 2005, we founded the RoboCT, the Inspector Rob company, because we are not allowed to resell products, as I mentioned already. And in a research project, for our flagship project, we were developing RoboCT especially on topics for large castings. And then once we get a call, some large companies coming by, because he is interested in doing 2D inspection and also want to have 3D capability for development. And then with high-tech, we performed very good, and the first RoboCT for large casting for development and also for automated testing was delivered last year, somewhere around November, December, mid of 2025. Yeah, so that's the story. So from almost 2005 to 2025, so it's 18 plus from the first systems. And now I would like to show you some scientific applications we did in our lab. What we're running two beams. So we have one 225 kV source with a mesofocus. And we also have now the opportunity to work within 450 mesofocus. Yeah, and the special thing is, yeah, we could run with 15 micron. And that was the first scans we performed. That was performed from Wolfgang he performed a large scan. He's passionated the airplane glider, and they have some issues with one of these airplanes. And while we have some public events, he said, yeah, why not scanning this air glider and check what's inside? And he also performed first CT scans with a mesofocus, and that's really quite impressive. So maybe it could be a good, not perfect scene. So the arrow shows the tip of the wing. So L steht for the left side and OB for the other side. And that's some kind of touch-up pen. And checking what dimension does a touch-up pen delivers. It's something about 15 to 100 micron. And that's 180-degree axial CT scan with a mesofocus with our RoboCT. And that's quite amazing results. Yeah, next thing is all about battery packs. So also now with the 450 kV, we are able to run or scan battery packs. And we already seen the approach. The approach is we perform at first step a 2D large area scan. That could be very quick. So in this case, 20 by 18 images. So 18 minutes scan time and stop and go, of course. And yeah, could see a lot of details. And then the next step, you could say, yeah, I would like to have more depth information at this position. I could also throw these kind of projections in an algebraic reconstruction technique. And now I could see more detail at what depth the wire, for example, for this temperature sensor are located. And of course, in an additional step, if you would like to see more resolution, and that's a quite impressive thing, that's the first lambography we performed with our 450 kV mesofocus, somewhere around 37 micron resolution, and that's high resolution CT is applicable for RoboCT in a certain range. So I think large casting, that was the big step. That was also the first step we done with BMW at that time. So escalating strategy, so we're scanning with 2D, doing 2D RDR inspection, and if there is some area you have to more look at in deeper style, you could perform a CT and could see if it's really critical defects or not. Yeah, coming to the conclusion, summary and outlook. So I think over the last year, RoboCT is a tooling that could be used in daily use for applications. So, and especially the advanced trajectories, the arbitrary trajectory, we are able to move with the RoboCT while we do not really have limitations on the dimension and the size and how to put a large object on a turntable. We could show and demonstrate how powerful RoboCT is nowadays. So RoboCT is no longer in its infancy, it's now mature and proven technology. And yeah, I think Gabriel here shows a lot of topics, some topics, 5 great topics that have to be solved. And Frank already mentioned in this conclusion this morning, if all the technologies we are now developing on RoboCT would be available on a classical CT, everybody would be very, very happy. Just put in a part, press the button, and your result is coming 20 minutes later. Thank you very much.
Thank you also very much for a very interesting topic and very interesting speech. And we are ready for answering your questions, if there are any. Everybody is looking forward to have a coffee. Well, perfect job.
Perfect.
Thank you very much.
You're welcome.
And yeah. And ladies and gentlemen, we will now take a short coffee break until 3 p.m. Please feel free to enjoy the coffee on the left side, on the right side from your angle. Also feel free to visit the booths of our sponsors and the poster area in the laboratory hall. We will begin with the program, as I said, at 3 p.m. with automated decision-making in quality control, a modern entity perspective by Mr. Markus Soss from the University of Augsburg. So see you soon, enjoy networking, and thank you for your attention.
got me pacing left, right, backwards, forwards and back again. Stressing, I'm about to lose my mind. I'm watching old home videos, the tears flowing and I'm sipping slow. Wishing it was this easy to press rewind and go back in time. Go back in time. Go back in time. Go back in time.
and gentlemen, may I kindly ask you to take your seats as we are about to continue with the conference program in a few moments. Ladies and gentlemen, may I kindly ask you to take your seats as we are about to continue with the conference program in a few moments. Specifically, there was missing one speech by Mr. and he will be presenting tomorrow. He will be presenting tomorrow at 11:30 to 12, and this one was missing as original version. So specifically for that little mistake. And now we can move to our next speech. Ladies and gentlemen, it gives me a great pleasure to call upon Professor Markus Sausen, Professor of Mechanical Engineering at the University of Augsburg and Director of the Center for Future Production. And in his talk, he will hear about intelligent, self-monitoring production systems. The key highlight is the installed Markus Sausen, Professor of Mechanical Engineering at the University of Augsburg and Director of the Center for Future Production. And in his talk, he will hear about intelligent, self-monitoring production systems. The key highlight is the installed Markus Sausen, Engineering at the University of Mechanical Engineering at the University of Augsburg and Director of the Center for Future
and therefore is something, well, typically way different to generative AI. Nevertheless, it's as impressive and powerful in what can be achieved using those tools. And as said, we're doing that for over 6 years now, and I can tell you there's huge potential and we should pay attention. Now, just recently, if you're following that, despite of all of the other disasters happening in the world, there's also this little disaster here, the dark factory, a concept which of course is built upon AI and driven by automation and of course robotics, and I would even guess RoboCT. So you will find that in a dark factory, because the whole intention is to make that, well, ready for a fully autonomous system without involvement of the human. So that's why it's called dark, so you can turn off the light because the robot doesn't need. And X-ray provides its own light. So nevertheless, at least for me, as a German, as a European, I don't think that's probably the right concept for industry as it is here. It's probably having its justification for mass production, for sure. It's also having its justification to a certain level. But I think there is a better concept that we should tackle in Europe. And unfortunately, we've heard about Industry 4.0, but I'd like to go one step further. So I'd like to introduce Industry 5.0. I'm not the only one that's doing that, but as said, we paved the way already 6 years ago, and just recently also the European Union came across the idea to coin it like that. And while many of you are doing already Industry 4.0, that's good, and I'm not against it at all. It's just building the backbone of the next step, and that's what I'm going to talk about. So that way, that's the 3 pillars typically that are associated with the next industrial revolution that we want to build. There's sustainability involved, there's resilience involved, and there's a human-centric perspective. The latter one might be quite appealing in the context of RoboCT because, of course, the robotic system is working autonomously, intentionally, but what's the place of the human? How can we build that with the human integrated in all of that automated process? Sustainability, on the other hand, looks like a green touch. Of course, that's inspired by that, but given the geopolitical changes we face, it might be quite a good idea to become somewhat sustainable on resources and energy anyhow, and the same is true for resilience, but I'm not going to touch too much into those fields, just in case. So, actually, we started with that AI production network a while ago. We said, well, it would be smart to do AI for industry, and we expected a little amount of money from the Free State of Bavaria. Technically, they gave us 92 million euros. That was quite cool and impressive, and we gave it a start, because we were able now to build that in real. And that's what I'm going to show you in the first video here. That's our little factory in Augsburg, Halle 43, and here is a little first look into it. So we're operating a real size factory with, of course, many robotic systems. We're looking into various processing technologies that are inspired, of course, by the companies we're working together. There's lots of things to say about data, of course, and of course, we're also having a RoboCT, so that's why all of that comes closely together. So, saying so, there is quite some things to do, and also many things that have already happened, and it replicates many things we've heard about today: digital twins, asset administration shells, and so forth. Right now, this is leaving you with an overall turnover of 400 million euros project volume that we've already done in that context, in more than 200 R&D projects and around 800 companies involved. So I'm definitely proud of those numbers, but the key message is, if you ask me what I'm doing all day, I'm trying to keep that alive. So that's why I'm not going to do the deep dive on science in that context. So still, I'd like to go with you straight to the shop floor and tell you a little story of how I would envision RoboCT to integrate in that future industrial perspective. So basically, we will start our digital tour here. So that's machining operations, and this is of course where some piece will be fabricated. Usually there will be quality control, so there will be NDT somewhere. There is the RoboCT, so you can see it's also quite decently large. And there could also be other quality control in mechanical sense, which we also do by robots, but I'm not going to touch that point for today. So, starting our journey here, so we're producing some parts, and here we go with the journey in machining operations. So, hopefully, no, now it should start. Okay, so that's typical machining of any sort of metallic alloy, doesn't matter. What we're doing is data aggregation, also via acoustics. And in that case, we developed AI to basically, during the production, tell us whether the tooling is in the correct status. So if it starts to wear out too early, we would be able to automatically replace it. So the AI basically tries to map the images that you see from the microscopy as a ground truth to the raw data we get there via a machine learning approach. So that's just an excerpt. So the total undertaking is a bit larger, and it's also generalistic in the way that this model doesn't just work in that condition, it's working for many machines for various materials. But the key point is we would like to develop that production machinery to a level where it starts to report the decision-making engine, NDT, that there is a malfunction in the production. All the rest that will be made a decision on the databases will not be inspected anymore. So probably bad news for the NDT inspectors, but the idea is to sort out many things as early as possible based on data-driven decisions. So, meaning that machine says, whoops, that part might be wrong. Takes a data-driven decision for most of the pieces with hopefully decently good production settings, being right, not being inspected anymore. And the rest is then automatically picked and as a first stage data-driven decision brought to some sort of entity that now makes a decision if that product is okay or not. So, could say that's a black box. That's usually sometimes how we envision AI, but that's not perfectly true at all. However, I'm just mimicking like that because that piece, of course, should go into such a decision body, and then, of course, we will see that decision. And it will also be data-driven. Nowadays, of course, it could be the human doing the inspection, making a check in the box, and then we go for it. But, of course, there could be better solutions. So let's have a quick look what's happening. And I'm trying to contrast a bit like old school standard on the left and what the new route could look on the right. So if there is no strict regulation what method to choose for a given point, one of the first questions, of course, is what method do I use in order to find a given defect for a given type of product and so forth. So in the worst case, could look like that. Maybe there's some tool at hand that can also guide the inspector. Maybe it's the gut feeling of the long experienced personnel. All of that would be okay. But that's decision making, very likely state of the art. Of course, it would be smarter to transfer all of that domain knowledge, the manifest of course, standards that allow us what and what not to do, transferring that into an AI, driven by various databases, with the big difference that, of course, can scale. You can provide it across your various platforms and therefore makes a decision like the human would do at that point, and the outcome could be, of course, use a CT method for that given purpose. Accepting that, the next question that we also tackled in great parts today is, okay, now I know which method to choose, but how do I do that optimally for a given situation? So the part delivered to that machinery will be individual, so geometry will not always be the same, because I'm not doing standard inspection, I'm doing inspection on demand. So everything needs to be readjusted, and again, today, it's a strong involvement of the human doing that and finding the optimal settings. Of course, we envisioned that already, that robotic systems might be quite handsome to tackle challenges involved with different geometries, and also now with smart software capabilities find the right inspection settings to fulfill a given task. Not just for finding the defect, but also for finding it efficient and economically affordable. So, here's a quick look into our setup. It was just spoiled in Markus Eberhorn's presentation, so we're the first customer of Inspector Op. So it's quite recent, despite of the fact that I'm into CT for 15 years by now. But this is just quite new in our facilities and ready to go. And here's a quick video look into it. So, of course, we're expecting that all of that planning procedure will be AI-assisted or software-sided at some point. So I'm glad that I heard from BMW today, at least it's not yet possible, so why don't we get there? So would be quite some idea to be faster on that. The testing for sure will also be driven by optimization. So we've seen the reinforcement learning approach just earlier, so that would be quite the right target to optimize such a trajectory for the actual inspection. In that context, AI can of course give you some assistance, can be fully automated, but at the end of the day, of course, the result from that scanning needs to enter the decision level. And as just stated, until now, that's of course the responsibility of the human inspector to make that decision at the end of the day. In the future, nevertheless, I would expect that there's also some simplification or advancement of that approach, which keeps the human in the loop, but still, of course, allows the actual algorithm to assist in that task. So here we still see some fancy images on that system in operation. Actually, it was a mock-up by that time, so just to tell you. Otherwise, it would have been hard since yesterday to actually get the video. So, well, at some point you get the data, volume data, 2D images, whatever. And again, the task of the human right now would be to do the inspection comprehensively, to all of the reporting, bring that down to Earth, and of course supply that data to the next level. We did some assessments together with inspection personnel, and effectively figured out, well, some not so surprising fact. I'm not sure if you ever thought about it, but I just realized, of course, there's a strong difference between a human doctor doing a treatment and an NDT inspector. Because there's a strong bias. If you have a human have a feeling that something's wrong with you and you go to the doctor, it's very likely that that person will find something, and that's quite rewarding and satisfying for that person. In production, unfortunately, we're very good, and usually 100% inspection would still demand that everything needs to be inspected, so every piece that shows up just annoys the person because the likelihood that something will be found is effectively quite low. And from the psychology point of view, saying a human-centric approach actually doesn't look like that. So it would be quite interesting to just replace that basic part and reduce the input to the human to a level where that person actually has a rewarding job and can actually find something. And that, of course, would be the fulfillment task for AI algorithms that do pre-processing of the data up until a certain decision level. So it could look like that. So you might barely see the markup here, but the idea would be for sure to, of course, give some highlight in all of that ton of data to attract the attention of the human and have a closer look at that spot, very simply. I'm quite aware that this is involving quite many ethical challenges, by the way, so we're also involved on that, but yeah, that's certainly where we want to go, because just contrasting back again the fully automated approach without the human, as of now I have some doubts that it would be the better route for the time being. So, after decision is made, we're, well, basically having a decision-ready system. If it's the human inspector, it could be that the part, of course, is removed and is not approved from that inspection, which translates in the word trash. So you're losing revenue, and therefore it's not intended. And most of the time, I would guess there's no consequences at all if such not approved parts are declared. So a closed-loop system instead would now take the inspection result and immediately feed that back into your production line. Meaning, if there's a deficiency that could be tracked back to a certain origin by an AI algorithm, could of course lead to the consequence that system starts to immediately adopt. And technically, that's what we're also doing in several projects. We're trying to close that control loop from such an inspection system to immediately adapt to production. In the best case, also with the prognostics involved, so that we're not actually even waiting until something is out of tolerances or not approved, but we're actually already looking for tendencies and then starting to adapt production immediately before we even get into that level that any part is not fulfilling all of the requirements. So, meaning that could happen technically in an instant in such a software-sided setting, and would then drive our machining operation in that way that everything is adapted quite nicely and then starts to change process parameters or starts to change a certain stock or raw material intake so that the production at the end of the day comes back all the time with good enough quality. So, with that little inspiration in mind, as said, it was not a deep dive of RoboCT, despite of the thing that I see that as a very strong decision-making entity in all of that chain, in the capability of the way how it's automated, the software-driven aspect, and therefore then also quite nice to work on that together with you. I hope there was a little bit of inspiration from that. If not, I'm also happy to take criticism on that part, but otherwise I'm just looking forward if you have any questions or want to enter discussion. Thank you very much for your attention.
Thank you very much. And as usually, we want to hear your questions, if there are any. Thank you very much.
Yeah, this is quite interesting issue. We have started at DIN, German Standardization Institute, to try to do standards for artificial intelligence. And due to explanation on non-destructive testing, there was a simple question raised. What is the qualification which the person who signs needs? My personal experience is, for instance, in radiography, I have different AI models, and they are work in a different quality for different machines. So I can evaluate if it's good or not. But the presentation that makes the impression that the knowledge of the person can go down and down and down, which probably you did not say, but that was the feeling when I did hear that. So what is the qualification of the people who can install that for industry like aerospace, for instance?
Yeah, I mean, that question whether or not we're reducing our skill set based on the usage of AI is a very generic one, so I'm pretty sure that's not limited to NDT only.
I only know NDT.
Yeah, I mean, I have two opinions on that, to be honest. The first one is, of course, like with every technological advance, there will be skills that we, on the broad basis, will no longer need. I mean, if anyone of you can ride a horse, that's great. I think it was a very worthwhile skill at some point in time, but meanwhile, it's no longer necessary in general. And I see that part of the route. But then there's the other one, of course, that's the responsibility you're touching. And I'm, at least, again, me as a human, when I'm entering an airplane, for instance, I would feel very comfortable if all the systems involved in building and operating that would be ready to a level that allows that to safely operate. And therefore, I would definitely guess the human that are involved to supervise such systems or install such systems, of course, should clearly know what they're doing. And I just want to repeat, the AI systems that we're using are not black box systems in general. So you can understand what they're doing, why they're doing, you can frame them, and there is ways to handle that. I can tell you, also on a mathematical basis if you want.
Well, it's a kind of blind. Okay.
I mean, it's the other thing is how humans are doing and operating with it, but I'm saying there's ways how you can properly operate it, for sure.
Okay, thank you.
Thank you for your answer. Don't hesitate.
Maybe the philosophy part is for the
Maybe
evening.
everybody is saving his question for a personal talk with you. Okay. If so, thank you very much. Markus Sauce and his talk. Thank you, Professor Sauce. And we are moving to our next speaker, and that's, if I'm correct, the last speaker of our today's program. The title of the speech is Next Generation CT Reconstruction. Ladies and gentlemen, I should like to introduce our next speaker, Dr. Darius Ruckert. Sorry, I will try to improve next time. CEO of Voxray and an expert in computed tomography reconstruction technologies. He focuses on developing advanced algorithms to improve imaging performance and enable next-generation CT applications. This presentation will focus on advanced reconstruction methods in CT imaging. Thank you very much.
Thank you very much as well. Good afternoon, everybody. I'm honored to have the last presentation today. First off, I want to give you a quick overview about our company. So we are still a quite young company with just 5 employees right now. We have started the development around 2020 and founded the company in 2023. And after that, we have launched our product, which is the QRT reconstruction, and just last year moved to our new office in Nuremberg. As I mentioned, our main product is the QRT reconstruction. I know the name is a bit fancy, it stands for quantum reconstruction. The name actually comes from because we are simulating the X-ray photons, and quantum is a fancy name for photons, so there's nothing about quantum computing or stuff like that. We are happy to tell ourselves that our reconstruction is the best reconstruction right now for difficult scenarios. Because we can handle all types of trajectories, we can handle difficult settings like multi-material scans and very noisy settings, or if you only have very few projections. Of course, this all translates well to robotic CT, and actually in 2024, at the ICT conference, we have already published a paper on robotic CT. So this is pretty much the first thing what we did after the company was founded, to publish a paper on robotic CT together with Simon and Gabriel from TH Deggendorf. And this paper was about pretty much how to do CT reconstruction for robotic CT without the need of calibration. So this was the basic idea of it. And we did it also a test here at the system at Deggendorf and also at the University of Erlangen. And we pretty much showed that with like a software geometric correction, we can get very good results out of the reconstruction, even though the system is not calibrated very well. And the idea behind that one is our reconstruction pipeline uses what's called a differentiable X-ray simulation. And the differentiable means that we can also backpropagate gradients toward the geometry and therefore optimize the geometry during the reconstruction process itself. And of course, so this is the top left part of here, which we can use for that. And we can use this reconstruction pipeline to then do first what we call a global geometric correction. In this case, we are trying to find global parameters of the system. This is mostly used for circular CT systems. So for example, here we have had a problem at one of our customer systems. They actually managed to crash a large part into their X-ray source, which pretty much destroyed all the previous calibration of that system, and all scans after that crash pretty much looked like this. So here they did a helical scan of a battery and it was a bit washed out. So now what we can do is we can use this scan data, so no calibration phantom, just we use the scan data of the battery, we put that into our reconstruction software and try to find the global parameters of the geometry and try to find like which of these axes are actually like tilted, for example, or not good anymore. And in this case, we actually found that the motor that moving the sample up and down had like an error of around 2%, and this was the reason why the results were so off. So then we can just apply this like the correction of this motor to the system itself and then get good results out of the scanner again. So we pretty much fixed the system just using our reconstruction software. Furthermore, what we also can do is what we call the pair projection geometry correction. So in the previous case, we wanted to find like global misalignments of the system, but what you can also do, like for each projection individually, you can try to find like what is like a small change in the projection geometry. And here we also had I wanted to say a nice case from our customer, but what they did is they scanned like a biological sample, and during the scan time of around 2 hours, some of the water evaporated, and therefore the whole object tilted a little bit and deformed. Yeah, so in this case, the transformation or like the geometric error is not very, it's not like a global error anymore, because somewhere it's somehow deformed, yeah. And in this case, we used like the pair projection geometry correction. So on the left side, you can see how it looks like if you just do a reconstruction with a geometry you get out of the scanner. And if you optimize the pair projection geometry, you can actually get the scan, the reconstruction very sharp. And here the customer was very happy because he did like 40 of these scans, and we fixed all of them, and he did not have to scan all of these 40 samples again. Okay, of course, now this is like the perfect case now to use for the robotic CT, because in robotic CT, you always, or in many cases, you also have like some inaccuracies in your geometry. I mean, we had a few talks earlier that mentioned it on a side note, but in fact, like the geometry on robots is quite a big issue usually. And here we have one of our customers who is using robotic CT in our reconstruction software, and he is actually doing robotic CT without any calibration phantom. So what he does is he just puts in a part, in this case, let's say this aerospace panel of this rocket, and then he programs a trajectory. Let's say source go to XYZ position, detector goes to a different position, and these two positions are then put into our reconstruction software, what he has programmed in, not what is the actual position of the robot. Then our reconstruction pretty much does the rest. So we do the reconstruction of the part and also do the geometric correction of the robot in a single go. And here you can, on this aerospace panel, which was quite large, so this is like a typical example of robotic CT. It was like maybe 4 centimeters thick, but like a meter times a meter wide. And here we looked into the panel, especially what was interesting here is this the core of the panel, and they were interested first in the splice, so that was like the border where 2 of these panels connected. 3D, and we found actually that at some point, you can see it on the left side, there was like some missing adhesive in this core splice, so there was like a weakness found in this panel. Furthermore, these panels are quite interesting, and in that case I actually learned that rocket payload fairings actually have a cork layer somewhere inside from Portuguese cork trees, which you can see here on the left side. This noisy pattern is the cork layer. And they also have, like on the top and bottom, they have a CFRP layer. And here what like people from the aerospace industry found really cool is that you actually see all the small air voids inside the CFRP layer and some bright spots which are particles. If you look closely, you can maybe also see like the orientation of the fibers here as well. And this is all by the robotic CT system. What I personally think is really cool with robotic CT, so this is like I would say a typical robotic CT application. But what I find cool is that you can actually use it also for more standard CT applications. So in this case, it's a helical CT scan of this power drill. So this you can probably do also on most of the standard circular CT systems. But if you have a robotic CT, you can do both. You can do large aerospace panels, but you can also do regular CT scans. So in this case, again, this was scanned like in an uncalibrated way, so just put the rotation stage somewhere, put the drill on top, and just measure it by hand, and then put it into our reconstruction software. And if you would just like turn off the geometric correction, you get an image like here on the left side. So you can, with some imagination, see a drill, but pretty much all the edges are very unsharp. Once you turn on the geometric correction, now you can see the actual part very cleanly, and you see that all these geometric artifacts are pretty much gone. It's also quite nice to see in the 3D here, where on the left side, like all the surface is kind of broken, and with the geometric correction, you can fix all these little issues here. Then let's go to another part, which is more typical for robotic CT. Here, this is a motherboard of a PC, and I think what's quite what's quite nice is that with a robotic CT, it's actually possible to scan the whole motherboard in a single go, right? Because this is usually quite difficult to scan like this whole motherboard with a circular CT system in a high resolution, because if you turn it around, you would have to go further away from the source. But using like a robotic CT laminography system, you can get the whole motherboard into one scan. And this is what we did. So this was a large scan. You see it on the left. It was like 17,000 projections. And this is the results. And I mean, it looks quite nice from here, but it looks even nicer because you can, like, it's crazy how much you can zoom into this 3D scan. If you're interested, we actually have this gigapixel image also on our website where you can really zoom into like every part of the motherboard. I know people like it in grayscale as well, so here's the grayscale version of it, and it's nice that you can really see like for the whole PCB, you can see like every void in every soldering stage. Okay, so my last example from our customer is this here. This looks a bit wild. So what they did is they just put like several parts next to each other in the vault. So on the left side you have some aerospace part, and there's like a AirPod case. Yeah, then there are two PCBs. Then there's an iPhone and another aerospace part, and like everything into the vault. And then the robot like pretty much scanned all 6 parts like in one go, just to save time as well. And let's take a look at the first example. So the first one was the AirPod case, which you can see here. Of course, it still has some missing angles. So if you see like on the slice in the top left and top right, you will see some missing angled artifacts. But overall, the quality looks quite good. Let's zoom in here. And we can zoom in even more, and you can actually see, like, for the battery, you can see the layers. Maybe it's a little bit noisy, but still the resolution is quite good in this case. And then we can also, okay, this is the 3D rendering of the AirPods case. It has the AirPods inside the case, and it was scanned in this way. And then the last sample is also the iPhone, which was scanned in the same scan, yeah. So everything was scanned just in one large go. And here's, it also already looks quite nice, but if you zoom in, it looks even nicer. I'm maybe not sure if you can see it from the back, but you can actually see also on the chips, you can actually also see the wire bonds of these chips in this scan. And again, just a reminder, this was also done with an uncalibrated robotic CT system, just relying on our geometric software-based correction for the reconstruction. Okay, so finally, I'm also happy to announce that at our lab in Nuremberg, we have now a X-ray vault, as you can see here, and you can imagine what's inside. Yes, there will be a robotic CT system. It's not completely done yet, so as you can see, there's the detector missing. But once But once it's up and running, I'm also happy to invite if anybody wants to take a look. You are happy to come by and check it out. So this system is then used mainly for us to improve our software, and then also for research, because this is actually located at the University of Erlangen-Nuremberg. So we can do research as well as further improve our software on that one. So if you're interested in trying it out for your own robotic CT system, please let us know, and we can hook you up with a trial license of the software. Thank you very much.
Thank you also for your presentation, and there is again room for a discussion. If anyone of you want to ask a question, please raise your hand. Our microphones are ready, and I see 1, 2, the last row first. Thank you.
Can I talk? Can you hear me? Thank you, Darius, for this very nice talk. A couple of pictures I haven't seen yet. About the motherboard, I wondered. You said it was a laminography scan.
Yes.
Therefore, I assume the exact side view of the board was missing in the data. Yet your pictures, they seem pretty scarce of known laminography artifacts. Would you say that your software is particularly capable of compensating those artifacts? And if yes, how does that work compared to the self-alignment?
Yeah. Okay, so if I would show you from the motherboard, like the 2D slice in the side view, you would see artifacts, right? So it was a little bit hidden by the 3D rendering. This hides quite a bit of artifacts in like careful thresholding. But anyways, it was still, of course, our reconstruction also helps in reducing these artifacts a little bit, and also the scanning setup was done in a way where there's like the least amount of artifacts that out there. But if you would look in the 2D slices, you will still see laminography type of artifacts. Yeah.
Thank you. And I've registered another raised hand. Thank you.
Thank you for an excellent talk. I wanted to ask you whether your system will be able to handle multi-channel data for photon counting detectors with multiple channels or even spectral. And another question, which is probably more simple, how many actually projections and what was the size of projections you have taken for this complete scene with this i4 and this bag and those things? How many data? How much data?
Okay, so first question. So so yes, we have. So we did couple of trials with photon counting detectors already. However, we have not been using like all different channels into the same reconstruction yet. So far, like we did like separate reconstruction for the different energy thresholds of the photon counting detector. That works well so far. The large scene with 6 samples at the same time, it was also around, I think, so it was like around 3,000 projections per sample. So times 6, it was around 18,000 projections in total.
And what is the duration of that scan? How long did it take?
I actually don't know. That was done by our customer, but I would assume that was done like overnight. So just from my guess. Yeah.
Thanks. I see no other hands. Okay. In that case, I will thank you very much for your presentation. Thank you, Doctor. And that was, ladies and gentlemen, the last presentation of first day of our second RoboCT UserForum. But we are not finished yet entirely. Please let me inform you about the poster session which will take place until 6 p.m. in the laboratory hall next door. where you can inspect not only the samples but also the work of your colleagues. And you are warmly invited. Warmly invited to explore the posters, meet the authors, and engage in discussions on ongoing research and practical application in robotics CT. At the same time, we encourage you to visit the booth area in the background, and our partners and sponsors are ready to present their last technologies and solutions. And allow me also to take this opportunity to invite you to the networking dinner that will begin right after the poster session at 6 p.m. again here and in the laboratory hall next door. The evening will provide a relaxed and informal setting to continue your discussions. Looking forward to tomorrow. Also, I just remind that we will begin at 9 a.m. here. We will begin again with welcome coffee, and the first presentation will begin at 9:30. It will be again 6 speakers presenting a range of advanced applications. Once again, let me thanks to all organizers from the Technische Hochschule Deggendorf, as well as all sponsors for making the poster session and the evening program possible. We look forward to your active participation. Thank you very much. That's all for me for today.